All right, welcome. Today we're going to tackle two really powerful, sometimes tricky concepts in C programming, recursion and file handling. We're going to take these abstract ideas and show you how to forge them into real, professional, working code. So let's jump right in. Okay, first stop on our journey, we're diving head first into the abstract. We're going to wrap our heads around the elegant and, yeah, sometimes totally mind-bending idea of recursion.
Okay, to really get this, I want you to imagine something. Picture a long street with two giant mirrors facing each other. You know that infinite reflection effect? That's our hall of mirrors. Each reflection is just a smaller version of the one before it. Recursion is like walking into those reflections, one after another, going deeper and deeper, until you hit the very last one, the one that doesn't reflect anything else. That's your end condition. And then you turn around and walk back out. And as you pass each mirror on the way back, you pick up a piece of the answer. That right there is recursion in a nutshell.
Now, for the computer to keep track of this walk through the mirrors, it needs a sort of breadcrumb trail, and that's called the call stack. Think of it as the computer's short-term memory for this trip. Every time you step into a new mirror, or in programming terms, every time a function calls itself, the computer jots down a quick note like, hey, we're in mirror number 3, and puts it on top of a stack. That way, it always knows how to get back out. So let's connect our little story to the actual code. The mirror itself, that's your recursive function. The act of looking into the next smaller mirror, that's the recursive step, the part of the code that calls itself. And that final mirror at the very end, the one that tells you to stop, that is so important. It's called the base case. Without it, you'd walk into the reflections forever. The call stack, as we said, is the computer's map. And what happens if you go too deep? Well, the computer runs out of space to leave breadcrumbs, the stack overflows, and bam, your program crashes. That's a stack overflow.
Okay, so we've got the big idea, the whole Hall of Mirrors thing. Now let's see how this actually translates into C code you can write and run.
Which brings up a good question, right? Is recursion just some clever academic trick, or is it actually a powerful tool you should have in your toolkit? Well, the answer is it's both. Here's the deal. You absolutely should use recursion for problems that are naturally recursive. Think about things like navigating a file system directory or tracing a family tree. These problems just scream recursion because each part is a smaller version of the whole. But, and this is a big but, don't use it when a simple loop will do the job. Trying to use recursion for like a basic countdown from 10 to 1, that's just overkill. It's less efficient, and like we said, you risk that dreaded stack overflow. Let's make this concrete with a classic example, the factorial. So if we want to find the factorial of 4, the function basically says, I don't know that, but I know it's 4 times the factorial of 3. So it calls itself to find the factorial of 3. That function says, I don't know, but it's 3 times the factorial of 2. And on it goes. This is the going down phase, walking deeper into the mirrors. We go from 4 to 3 to 2 until we hit our base case. For factorial, that's 1. The factorial of 1 is just 1. Now we stop and turn around. This is the walking back phase. We pass that answer, 1, back to the previous call. It calculates 2 times 1 is 2, passes that back. The next one calculates 3 times 2 is 6, passes that back. And finally, the first function gets the 6 and calculates 4 times 6 is 24. Boom, we have our answer. And here's what that looks like in C. It's surprisingly simple, right? That if n equals 1 statement, that's our base case, our stop sign. And the else block with return n times factorial n minus 1, well, that's the recursive step, the part that looks into the next mirror. And over on the right, you can see us compiling and running it. And yep, just as we expected, the factorial of 4 is 24. Okay, let's try one more to really lock this in. How about summing the digits of a number? For this, let's switch our analogy to a street address, say 237. We're going to use two simple math tricks here. The modulo operator, that's the percent sign, gives us the remainder of a division. So 237% 10 gives us 7. It basically peels off the last digit. Then regular old integer division, 237 divided by 10, gives us 23. It lops off that last digit. See how that gives us a smaller version of the same problem? So let's trace this out. We start with 237. The function says, okay, I'll hang on to the 7, and I'll ask my little brother what the sum of 23 is. The next function call gets 23. It says, all right, I'll hang on to the 3, and I'll ask what the sum of 2 is. The next one gets 2, hangs on to the 2, and asks for the sum of 0. Aha, 0, that's our base case. It just returns 0. And now we walk back.
The function that had the 2 adds its 0 gets 2. The function with the 3 adds that 2, gets 5. And the original function with the 7 adds that 5 and gets our final answer, 12.
And look at the code for this. It's so elegant. That single return line does everything we just talked about. It says, just give me the last digit and add that to whatever the sum of the rest of the digits is. It's beautiful, right? I really encourage you to play with this. Go into that main function, swap out 237 for any number you can think of, and watch it work.
All right, so if you're going to write your own recursive functions, there are 5 pro tips you absolutely have to live by. Let's run through them real quick. Okay, number 1, always have a base case. That's your escape hatch. Without it, you're creating an infinite loop that will crash your program. Guaranteed. Number 2, make sure you're actually making progress towards that base case. If your problem isn't getting smaller with each call, you're just spinning your wheels. 3, if you get lost, draw it out. Seriously, visualizing the call stack like we did with the mirrors is the best way to debug. 4, be lazy. Watch out for solving the same exact problem over and over again. This can make your code incredibly slow. And that leads to number 5, memoization. It's a fancy word, but all it means is saving the results you've already calculated so you don't have to do the work twice. It's like writing the answer on a sticky note. So we've spent all this time looking inward at functions that talk to themselves. But what good is a program that can't talk to the rest of the world? It's time to look outward. And that brings us to the next chapter of our story, the programmer's diary. We're going to expand our toolkit and learn how our C programs can actually read from and write to files. In other words, how they can listen and speak to the outside world.
So our new analogy is a simple diary, and using it has just 3 steps. You've done this 1,000 times. 1, you open the diary. 2, you either read what's on a page or you write something new. 3, you close the diary. Simple. In C, the file pointer is basically your bookmark, keeping track of where you are. The fopen function is what opens the book. fputs writes in it, fgets reads from it, and fclose closes the cover. And I'm telling you, that last step is so important. If you forget to close your diary, your brilliant new entry might just disappear into thin air. Let's look at the actual code for this. fopen is your key to the diary. You tell it the file name and the mode, like R for read or W for write. Then you have functions like fgets to read a line or fputs to write one. But listen, I have to give you a huge warning about that W mode. Using it is like ripping out all the old pages of your diary before you start writing. It will erase everything that was there before, so be careful. And finally, there's fclose. Please, I'm begging you, always close your files. It's how you save your work and tell the operating system you're done.
Okay, here it is all together. Look at this example. First, we open mydiary.txt in write mode. Remember, that's the destructive one, and we write a couple of lines. Then, super important, we close it. Next, we open the exact same file, but this time in read mode. We read the first line into a variable, and then we print it out to the console, and you can see the output on the right. It works. We successfully read back, "Hello, Vanessa."
Okay, let's take a step back. We have recursion for handling complex, internal logic, and we have file handling for communicating with the outside world. We've got the tools. Now it's time for the final synthesis. How do we combine these ideas to build professional, scalable code?
Here's the secret. Professionals don't dump everything into one giant file. That's a recipe for disaster. Real-world code is modular. You break it into pieces. You have header files like main.h, which are like a public contract. They declare, hey world, here are the functions I offer, but they don't show how they work. Then you have your source files like factorial.c. This is where the secret sauce is, the actual logic and implementation. And finally, you have a totally separate place for your tests, which lets you hammer on your code to make sure it's bulletproof without cluttering up the main logic. So, when you compile your project, the compiler acts like a master assembler. It takes the public promises from your header file, links them with the private logic from your source file, and uses your tests to verify everything. The result is one final, clean, bug-free executable. This is the professional edge. This modular approach makes your code so much easier to understand, to expand, and to reuse down the line. It's the blueprint for building anything serious in C. And there you have it. We've gone from the mind-bending hall of mirrors all the way to the practical, organized structure of professional code. You now have the fundamental tools to write functions that can solve seriously complex problems and programs that can actually talk to the world.